As you know, BI and data science are about being curious and solving problems in different ways. This Graph Database Fundamentals course will give us an opportunity to do just that. Instead of fact and dimension tables, graphs are a network of nodes and relationships, with the most important difference being that the relationships are just as important as the nodes themselves. We'll be using Neo4j's Cypher query language to explore 4 different graph databases, which will help us understand specifically what types of questions they allow us to solve. We know you like having the opportunity to test your skills, so for this course, we've increased the number of exercises and challenges. By the end of the course, you'll be able to build a basic movie recommendation engine, as well as a shortest path optimization across the London Underground and even across Bitcoin's Lightning Network. One thing's for sure, graph databases can't solve all our analytical questions, but they give us a different perspective to help us think about problems in a different way. Let's get started. To download the Neo4j Graph Database Management System, just Google download Neo4j, click on the most obvious link for neo4j.com, and press the very obvious download link. Once you've done that, you'll have to enter a few of your details. Both personal and business emails seem to work fine when downloading Neo4j. Once you've clicked download, the file will appear in your downloads folder and you'll be prompted with this next screen showing you your Neo4j activation key. Hit copy to clipboard to copy this entire text string. Once you've installed Neo4j, you'll be prompted with this software registration screen, but you don't actually need to complete it and you can just press register later. At this point, the database management system is just initializing itself, and we're pretty much good to go. You'll know the installation is complete when you reach this main interface of Neo4j, and we're just starting on the project screen, which should have this example project loaded for you. The basic Neo4j interface is organized into a few different views, including the projects, the databases, and graph apps. But for this course, we'll mostly be working in the project view. Now, as we saw, you may have this example project already installed. But to make sure we're all looking at the same view, we're actually going to create a new project, hit new, and import a sample project from Neo4j. The one we're going to use is about recommendations. This will help us explore the concept of graph within a context that we're all familiar with. We'll explore movies, directors, actors, and then users who've actually reviewed those movies. So let's go ahead and install that. It may take a few minutes to complete, and make sure you choose which database version you want to install. And I would just pick the latest. So in this case, 4.4.11. Now, each time you create a new DBMS in Neo4j, you have to create a password. Now, as you begin your journey in Neo4j, you're probably going to be doing this many times over. So I suggest that you just use a simple password for the time being, such as 12345. Obviously, if you start using this for a production environment, you're going to create a more secure password. But let's go with that for now. If we click on the recommendations project that now appears, we can see that that's successfully loaded, and we can see a few files and documentation that's been used to create that database. Now, installing this may take a few minutes on your machine, so just be a little patient. Okay, so let's take a look at this recommendations database and see what this graph database is all about. First, click Start to initialize this database. It'll take a minute or so to do this, and then we'll be able to open it. And it's worth bearing in mind that you can only have one of these running at a time. We can see that the active database management system is now recommendations, and we're able to press the Open button at the top. This will bring us into a different view, which is where we're going to spend most of our time for the rest of the course. We've got the interface on the right-hand side where we're going to write our queries. The results of those will appear in this chain of results below, and we can open the main settings on the left-hand side using this top database symbol. In this left panel, we can see information about what are called node labels, relationship types, and property keys. We'll explore the theory behind each of those things shortly, but just to get started, I want to dive straight in and take a look at this database. The first pill within the node labels section indicates the total number of nodes within the database. If we click that, we get this example query that appears in the results. At the top, we see the cipher query used to generate what we see. We'll come onto the syntax shortly, but notice how we've got this limit 25 statement, similar to SQL, that's helping us limit the results that we see in our visual. We don't need to see all 28,000 to get an idea of what's going on. We can expand this results view using the button in the top right. And we can zoom into the results using Control and Scroll. At the moment, we see a very visual representation of our results. We're seeing some movie nodes, which we can see are blue, and we can see the genres that they belong to in orange. Those colors, the size of the nodes, and the caption that appears on them can be chosen by clicking on that node in the right-hand overview section. There is also a tabular view that we can see, which we'll explore a bit later, and this just presents the results in a different way. So obviously this graph is very visual. We can move around our results, we can drag nodes around to help us spot patterns, and we can even start to dig further into the database. So for example, the movie GoldenEye that we see here, if we click on that, we see these three buttons appear on the node. The bottom one, which indicates further relationships, helps us expand the graph to show more nodes that are connected to GoldenEye. If I zoom in here, what we can see is that we've got many different users that have rated this movie. So now we're showing two different types of relationship in this graph. We're showing movies that belong in genres, and we're showing users that rated a movie. So you can start to see how we've got this complex web of associated nodes that have different relationship types. And we can continue to expand. We can continue to expand and explore the graph database in the same way. It can be interesting to play around with this manually by clicking on each of the nodes as you go, but for most of this course, we're going to focus on cipher queries, which will help us return specific results to answer specific scenario questions. For example, what if I want to see the actors or the directors that worked on this movie, or perhaps which other movies they worked on? So we'll start to develop our queries to answer those questions. Now that you've seen one live example of a graph database, I just want to take a step back and look at the origins of graph theory. This will help you understand what types of scenarios graph theory and graph databases are really relevant to, and therefore what sorts of problems they will help us solve. In 1736, Swiss mathematician Leonhard Euler published a paper discussing route choices in Königsberg. Königsberg was built on the banks of a river, with part of the city being on two islands on the river. Königsberg also had a series of 7 bridges that connected each of these areas. And the question was, could you take a stroll through the city, crossing each bridge once and ending where you started? The paper that Euler wrote summarized his findings in mathematical terms and is considered to be the first paper published on graph theory. So how did Euler translate this city with its walks and its bridges into this concept of a graph database? Well, he proposed that the bridge problem could be summarized into a simple diagram using only vertices and edges. So we then have a different visual representation of Königsberg. If we take out the city and the islands completely and leave ourselves only with those nodes and the bridges, what we're left with is Euler's graphical representation of a graph. We have A, B, C, and D, which represent our nodes or the land masses, and we have the bridges between them, which are essentially the relationships. Now, over time, the notation has developed so that now, if we have a graph, we can say it's defined by its vertices and its edges, or its nodes and its relationships. So the land masses here are the vertices or the nodes, and they are A, B, C, and D, and the bridge connections are our edges or relationships, and we can define those as a long list of pairs of nodes. So we can say A and B are joined, A and D are joined, B and C, and so on. So Euler's paper was really the first time that the concept of graph was developed. And we still have that question of, is it possible to walk around this city, crossing every bridge and coming back to where you started? And we'll circle back to that question later on when we've learnt how to deal with relationships and paths around a network in our graph database. As the concept of graph databases has developed, there's also some additional notation which we can use to represent nodes and relationships. So we can define a graph with some additional parameters. We can look at this social network example. Each node in the social network has what we call a label, which is just a type really, and in this case we have two. We have user nodes, and we have groups that those users might belong to. Now each relationship also has a label or type. In this case we've got two different types of relationship. We've got the part of, when a user belongs to a group, they are part of the group. And we also have a follows type relationship, where one user follows another. And in this case you can see that some of those relationships are directional. And what you can see between the two users is that we can have multiple edges between two nodes. More generally, what you can see here is that vertices tend to represent things, whilst edges represent relationships or actions. This isn't strictly true of every graph, but it's a simple place to start. Let's recap before we introduce one final piece to the puzzle. So we have nodes which generally represent entities or things. We have relationships, which are the connections between them. Labels represent a type identifier for the node or relationship. But finally we have this concept of properties, which just gives us additional information about a node or relationship. Looking back at this social network example, we have these two users who each follow each other, but we don't know anything about these two user nodes. We can introduce these properties, so now we know user ID 101 is Mr. B, and user ID 201 is Meon. Now in a regular relational database, we're used to dimension tables that provide additional information about objects or users like this. But in a graph database, what we also see is properties about relationships. So we can see that user ID 101 follows user 201 since May 27th, 2021. And we can add all sorts of different information to the relationships like this. This ability to add properties to both nodes and relationships is why people talk about a graph as a database where the relationships are just as important as the data they connect. Let's take a look at some common use cases for graph. The first is for social networks. Now, social networks are characterized by a high number of nodes of the same type, which are typically users or maybe even groups that they belong to. Now, what we have in a social network is all sorts of different types of relationship, whether users know each other, follow each other, or belong in certain groups. The questions that this type of graph might help us answer are, who are the most important or influential users in the network, and how do these users know each other? When LinkedIn tells you who your common contacts are, you can think of that conceptually as a graph that's telling you how you might be linked to another user. So examples of these, obviously, Facebook, LinkedIn, Instagram, TikTok, all of them have a super high number of nodes of the same type, which are users. The second example I want to cover is navigation. In these scenarios, our nodes tend to be points of interest or junctions, which are linked by travel routes. And travel routes may, as they do in this diagram, have certain weights, such as distance, speed, or time to travel between those 2 points. The reasons this kind of graph would exist is to answer questions like, what steps should I follow to reach this point? So when you get a list of instructions on your phone telling you how to cross London on the Underground, which trains to take, and how to optimize your route, this is what it's doing. What is the fastest or shortest route? What parts of the network are congested? So examples of this are Google Maps, and we're going to take a look later on at an example of the London Underground. Next, we have money laundering and transaction analysis. And so in these examples, we tend to have entities, individuals, accounts, and documents linked by relationships that represent transactions, approvals, and even meetings. This could help us answer, where did this money come from? Who really owns this company? What transactions match this pattern of events? Or in payment routing, we might answer, via what route should we send this money? So common examples of this might be in banking. We'll look later at an example of Bitcoin's Lightning Network, and there was a particularly relevant example published in 2016 through the Panama Papers, which essentially exposed a whole network of offshore tax avoidance schemes using a graph database. The final example is one you may come across more often than you realize, and this is content recommendations. So the example I'm showing here shows different websites with different pages that belong to them, or pages that link to each other using hyperlinks across the web. We have users which visit certain websites or like certain pages, and websites belong to certain genres. So the scenario really has content, categories, and users as nodes, and associations, hierarchies, interactions, and ratings as its relationships. With this, we could answer things like, what are the most valuable pieces of content in the network? What is the most relevant to this user? What are they interested in? Or what recommendations could we make of what they should watch next? Google PageRank is a good example of this, as it constantly assesses all the content on the web, analyzing the connections between pages, ranking importance, and building in a user's previous behavior to decide what to display in the results. And whenever you watch Netflix, Disney, or any other site where you're consuming content, those sites are constantly making recommendations to you of what you should watch next. And so graph technology is one of the options that allows these companies to do that. Graph technology seems to have gone through a few cycles of being hyped, and then being ignored, and then being hyped again. It seems that the main reason for that is that people tried to solve too many problems with graph databases because they were the new thing. Graphs are good at solving specific questions in specific scenarios. So in the next video, we're going to look at what those common characteristics are that made the scenarios we saw in the last video good use cases for graph. The first is that often they have a lot of many-to-many relationships. If you've done any work with traditional data models and relational databases, you know that we try and avoid many-to-many relationships where possible. The second is where we have a lot of self-referencing entities. And what I mean by that is lots of users, for example, that refer to each other. They have relationships within the same data type. And so in a relational database, you would need all sorts of self-joins within a user table to be able to achieve the same thing. All of the examples we saw also had networks with multiple relationship types. This starts to bring in the main point about graphs, is that the relationships are just as important as the data itself. And not only can we have many different types of relationship in our graph, but those relationships can have attributes and properties just like the data. In a relational database, we're used to facts having additional attributes that we can find in our dimension tables. But in our graph, both nodes and relationships that mean how our data is linked is just as important as the data itself. There are 3 words I'm going to use to describe the types of question that we're asking. And this really means which nodes or chains of nodes share similar patterns. There are questions of connection. How are these nodes connected? And finally, we have questions of importance. And we can measure this a few different ways, perhaps looking at connections or frequency. So graph databases work particularly well to solve a very specific subset of data problems, but they can't solve everything. Often, graph databases are used with an extract from a relational database to answer maybe a specific question. Speed and efficiency on a graph are dependent on asking questions suited to this database type, but that's no different to a traditional database. The more suited our questions are to it, the better it will perform. So it's about picking the right tool for the task. Now that we've quickly covered the basics, we get to the exciting part. We're ready to start tackling some problems, so I want to talk you through the scenarios that you're going to solve throughout the rest of this course. We're going to be working with a movies database that connects movies with actors and directors, but it also connects with users and the ratings that they've given each movie. Using this dataset, you're going to learn the basics of cipher and graph, and throughout the chapter, we're going to build towards a basic movie recommendation engine. Next, Using what we've learnt, we will better understand how to navigate a graph with paths and circuits, which will allow us to circle back and solve the bridges of Königsberg problem. Now that is a fairly simple example, so we're going to take it to the next level and recreate one of the world's most complex train networks, the London Underground. And through this, we're going to learn how to optimize route choices using shortest path. Finally, I'm going to let you test your skills on a case study of the Bitcoin Lightning Network. So using this, you can test your skills on a fintech dataset and try to route payments via optimal paths. Don't worry, you don't need to know anything about Bitcoin to complete that task. To do all this, we're going to be installing a graph database management system, and there are plenty to choose from. We're not going to go into the details right now, but we're going to pick Neo4j, which is a leading graph database management system that uses a query language called Cypher. In Neo4j, I'll walk you through how to recreate each of our example datasets. This is a recreation of the Bitcoin Lightning Network, where we can see disconnected nodes, and we can see different relationship types between different nodes. You're going to be writing queries that help us solve scenarios like finding the shortest path between two nodes like this. The query language we'll be using, as I said, is called Cypher, and it does share a lot of similarities to SQL. It's just been adapted to answer graph questions more simply. So I look forward to going through the next few chapters with you, where we'll learn all about Cypher and we'll learn how to solve these problems.